Discussion on design patterns. So today we're going to be looking at design patterns that allow us to integrate different parts of the application or systems, or integrate with parts of an application that we don't own, that might make it more convenient to provide some different implementation. Well, not implementation, maybe a different interface that might be more convenient for us. That we don't have access to the actual implementation, but it would be convenient to consume that API in a particular way. For instance, it's oftentimes that we need to interact with a third-party API, but that third-party API might have a plethora of function calls that are very, very granular, and we would like to perhaps abstract it so that instead of us having to deal with the intricacies of multiple function calls, instead we could wrap 3, 4, 5 calls in a more less granular, right, more coarse API that abstracts the idiosyncrasies of each one of them into one very convenient method, right? That does all the work for us. For instance, when you're doing AJAX calls, it's actually a fairly intricate protocol, right, of handling multiple events, and so there are many libraries out there that just abstract the whole thing, right? So that instead of having to deal with all these intricacies of the idiosyncrasies of the protocol, they're abstracted at a higher level that handles all the nitty-gritty stuff for you, right? So you create some kind of an abstraction over it. So whenever you have these thin layers that communicate different parts of two systems, they're implementing a well-known type of design pattern, such as the adapter or the bridge or proxy, right? That try to mitigate the difficulties, the challenges of having these two systems, disparate systems, communicate, right? So that there's quite a bit variations of this meta problem, right? Of mitigating between two layers, but we see it all the time, right? Especially if you have multiple layers talking to each other, where you might have on the front end, you might have a JavaScript user interface that is talking JSON. In the middle tier, you might have Java, and in the back end, you might have a relational database. Between each one of these layers, there are adapters, right, that do the transformation between the layers, right, where you have some stream ASCII sequential representation of data that needs to be converted into a hierarchical, object-oriented representation instance in Java that then needs to be converted back into some flat representation in relational databases, right? So between all these layers, there's adapters or bridges, right, that do the conversion between these different layers and abstract it so that you don't, these things happen magically. You don't even realize them, right? And oftentimes are done by other design patterns, such as decorators, right? That you decorate and we've been using them in our projects, right? Where you decorate things as auto-wired, or as a service, or as a parameter, or as a media type, right? And automatically, right, the Java objects get mapped to JSON objects, get mapped to magically get mapped to tables and fields, right? So these design patterns are definitely applicable and relevant in today's modern programming languages. Some of them have become so ubiquitous that we don't even call them design patterns anymore, right? They have made their way into the language, right? And that's what it should do, right? languages are evolving, and as they evolve, they incorporate best practices that force you to code in a certain way, right? So the fact that Java doesn't support that has a garbage collector, that it has a single inheritance, that the packages names fit a particular data file structure. All these are design patterns, right, that have made their way into the language, and then it forces you to code that way. Now we have these injection, and aspect-oriented programming that have made their way into the language. But this is where they all start. They start as best practices in industry that people follow a particular style, right? And they eventually make it into standards, right? And then we kind of forget that somebody thought of this, right, as a good idea, and now it just becomes the standard way of doing things. Yes. So certainly these are just some of the more common design patterns. There's one that are specific to the Java language, or the J2EE component component technology, and surely you will be creating your own in your own practice. So let's just look at some of the ones that we have academically identified them as good ideas. So there's the adapter, as I mentioned, mitigates the communication between two layers, where one of the layers might provide a particular interface or a particular functionality that we want to convert or adapt to our liking. Right? And there's two ways of implementing them, either by inheritance or by composition. So inheritance, you would inherit from a base class and provide your own implementation of an agreed upon interface, overriding the base class's implementation of that interface. Right? Whereas in a composite, you would in a composition, you would use instead an instance of that object, and then you would you kind of proxy. You would create implementations in terms of the instance of the base class. So let's take a look at some examples of this implementation. So here's the class diagram for the adapter class. You have a you have a target implementation that you want to use as a different implementation, implemented by an actual adapter, right? But your coding, the client is only aware of the base abstract class. It doesn't know what the actual concrete adapter, how it actually implements it. You can change different adapters with different implementations, but you all only compile to the high-level abstract class. The adapter overrides all the implementation of the specific of the underlying implementation. So the client is never aware of the base implementation because they are overwritten by the adapter. So there's one way of doing it. You inherit and then you use the adapter's implementation. The object implementation is fairly similar, but instead of inheriting from the base adaptee, instead it implements the interface that you declare, and the adapter has an instance, right, to the original API, right, and it just uses that instance of the adaptee so that when you call the request, it calls adaptee dot and then the specific request, the actual implementation for the base class, for the adaptee class. Right. So the target is the interface that the client wants to use. It says this is a more practical implementation, and certainly there's plenty of these. Like JDBC is an example, right? JDBC provides an abstract implementation for connecting to a database, right? And it provides getting a hold of a connection, getting a hold of a SQL statement, and getting a hold of a result set, right? And iterating over it. But it only declares a base abstract class, which then all the various vendors give you different implementations of that, which those are adapters. Those are each one adapters. But the client is never aware that it's using a MySQL adapter or an Oracle adapter or a SQL Server adapter. It only sees the abstract interface, which is javax.SQL, right? javax.JDBC, right? So it never knows that underneath the adapter is of a particular class, right? So typically these adapters are the adapters are free to decide whether they're going to use inheritance or they're going to use composite implementations, right? From our point of view, we only see the adapter. We never actually see how it's implemented internally, and we shouldn't. From the client's point of view, we should not care on the actual implementation. So here's a trivial, simple example of implementing one data type in terms of another data type, right? Where we have a very generic data type of an array or a collection or list, right? But then you want to implement a more restrictive data type. Right? So for instance, you could implement a stack, right, or a queue, right, which is basically just a collection of items, but you're restricting the types of behaviors that you have, right? That you can only manipulate the collection from either end of the collection, right? A queue that's a good question for an exam. You have a queue and you have and you can manipulate it from either end of the collection, and the stack you can only manipulate it on one end, right? You can pop and push. In the queue you can dequeue and queue, but you can never, for instance, insert in the middle, right? That would defeat the purpose of the queue or the stack. But you can certainly implement it on top of something that is more generic, like just an array. Right? Arrays allow you to certainly manipulate on the ends, but also in the middle, or lists, or collections, or array lists, or any of these, right? Or hash table, right? Or hash map. So any of these more generic data types could be used as a base implementation for a more restrictive adapter, right? So here's a simple example of implementing the stack or queue, right? In terms of, in this case, a vector. So even though the internal implementations of a vector allows you to arbitrarily modify the collection from anywhere, right? The stack would allow you only to implement, manipulating up from one end of the collection. So we certainly can implement one in terms of the other, by just inheriting from vector, and then you can implement push, pop, and size in terms of the functions that we inherit, right? Our new adapter class, stack adapter, can implement pop, push, and size in terms of the inherited function methods. So here we have vector that declares its own interface, right? Of inserting at any place, or element add, remove element add. So this is the typical the base implementation. So this is a specific detailed implementation of a particular less abstract, more generic class, from where we can then implement a more restrictive implementation, such as a stack. So the stack, we decided that this is the interface that we want to use. In this case, just push, pop, and size. And so what we would like to be able to do is write our client in terms of this data type, so that it's unaware of the actual implementation underneath, right? So we'd like to implement against this interface. So here's our adapter, right? Our stack adapter that inherits from vector. So we get all the base methods, right? We get the size, we get the you get size, element at, right? You can insert anywhere you want in the vector. Plus, we're implementing the stack interface, right? So we have to provide implementations for those three functions: pop, push, and size, I believe. Yeah. We inherit size, so we're gonna be overriding size, right? Or actually, no, I think we can use just size, and that's it, right? I think maybe we could implement a couple more, maybe empty. Is it an empty stack, right? So that would be a good part of the interface. So yeah, so push here we're just writing it in terms of the methods that we have inherited from vector. And pop, again, we're also writing in terms of the size that we inherited and the remove elements that we have, remove element at that we have inherited. Here's a couple more. This is the object implementation. So instead of inheriting from the base vector, we instead have an instance of the vector, right? And we write the push and the pop in terms of the functions of the instance of the adaptee, right? As opposed to having it inherited. Right? So yeah, two different implementations. From the point of view of the client who's using this, it's irrelevant. Right? The adapter is free to use one or the other. From the client's point of view, they just get the adapter. Right? They don't know that internally they're using inheritance or composition, and that we shouldn't. Right? As a client, we should not care how is it that we are implementing it. Right. So the class adapter uses the inheritance. Although if you have a long list of hierarchical inheritance, then it complicates things, right? Since the adapter only works on the class that you're inheriting, right? That if you would want to, if you have a subclass of those, you would need to inherit from each one of them. So it would become fairly complex. You would have like a parallel hierarchy of adapters, right? That you would have to adapt each one of the different classes that are being adapting. Instead, objects, you can have just an instance of the class that you want to adapt, right? Which can have all the implementations of any of the classes that it's inheriting from. So it's a little more convenient in that sense. You can also pass it as an argument. Right? You can pass the adapter that you want as an argument, or it can be calculated on the fly, right, at runtime, which is basically what JDBC does, right? In JDBC, you can give it a string of the class adapter that you want, right, and it can instantiate on the fly an instance of the adapter that you can use, and then pass it as an argument and say, well, this is the adapter that I want to use based on the vendor that I want to talk to, right? You can either drive that as an XML configuration file or as a properties file that you can read from, right? And then you can instantiate it on the fly. So so object adapters are a little more versatile in that sense, that you can decide this at runtime. Bridge is almost the same idea of the adapter. It basically wants to be able to have two parts of an application be able to communicate with one another. That you want to decouple these implementations so that you can change and modify one of them without having to modify the other. Yeah. So the idea is that you don't want to be bound, right, to the actual implementation. You don't want to know anything about the underlying implementation because then you would be dependent on that implementation. Right? You don't want to break the information hiding principle. Right? That once you know of a particular implementation, you are then married to that implementation. Right? So if you know that underneath they're using vectors, and now you're relying on the fact that they're using vectors, that means that now the base implementation can't decide to change its implementation to maybe use linked list instead, right? So when you couple these two, modifying one would result in also modifying the other one. So ideally, you want to code in such a way that you're only coding compiling to an interface, so that you're not dependent on that. So one way to do that is that instead of the parent relying on the children and knowing their implementation, this could be inversed, right? It could be or reversed in such a way that the parent can pass an instance of itself to the child, right? So that the child and the parent implement a particular interface, right? And so the child can then rely on the parent implementing a particular interface, and then the child can then have the details of the implementation without the parent having to know the details of the children. So you can spread over, kind of change the relationship or the responsibility, right, on each one of the childs of the actual implementation. So let's see an example. So here we have a base class window, where you have a window. You might have multiple classes that inherit from it. And you have when you want to add a new type of that implements the base class, you have this explosion of multiple classes that are inheriting from this. So instead, well, let me see. Let me just look at this. Right. So here we have a stack type. And it's an enumerated data type, so that means that a stack type can either be implemented as an array or a linked list. And we're going to try to compile against the same interface that we had earlier. And then depending on the type, we can decide to either use arrays or to use a linked list. Here we have main, and it's providing the stack type that we want to use underneath. Right, implement the stack depending on the array, and depending on the type that we're passing here, the enumerated data type, internally we can decide whether we want to instantiate an array, or we can instantiate an array list for the local implementation. And then depending on how we decide depending on that enumerated data type, the pop and the push, it will be either using lists. Linked list where you tie the pointers or references, or an addition or adding to the array list, the underlying array list. Now this implementation is going to be fairly cumbersome. Let's see. Here we have a case, right? And depending on the type of the implementation, whether we pass in array list or we pass a linked list, we would implement one or the other. We would instantiate one or the other, but both of them, right? These linked list based stack and array based stack, they both are going to implement the underlying interface, the stack interface, right? Both are going to be implementing push and pop, but they're going to be implemented differently, right? The actual concrete implementation of the linked list based stack and the array-based stack, they're going to implement push and pop differently. Right? So this impl will either be one or the other, and the implementation is going to be different. So let's take a look at the implementation for either one of them. The array-based stack obviously is going to use an array to add at the end of the array, right? Where here when we push, we're going to use the square bracket nomenclature. That at the end of the array we're going to add this new element, whereas when we pop it, we return the size -1, and we keep an instance of a generic object, right? So we can store any object in there, right? And whereas the linked list is going to have references in multiple nodes that are linked together, right? Where each node has a reference to the other one, right? To the next one, so we can follow along. It could be a singly linked list. It could be a doubly linked list. In this case, I believe it's doubly linked list where each one of the nodes has both a reference to the next and the previous, but we only keep track of the tail. So because we're only adding on one end and we're removing from one end, we only have to keep track of the last element that has been added. So pushing just adds to the last element in the linked list, and popping removes it from one end of the list. Yeah, so here's removing it from the tail. So typically, they're very, very similar to each other. Typically, adapters come kind of like a later time. Once you have already an implementation, and typically you cannot change it, right? You already have an implementation that's been either a legacy implementation that's been given to you, and you don't have control over changing that base class. So the only way is to adapt it, inherit from it, or have an instance of it. Whereas bridges are typically designed a priori, right? Where you want to create this communication between the two, and you implement this. Now, one way to improve this is that is to have these children be passed a link to the original stack, right? And the stack implement the pop and the pop and the push. So we'll see an implementation in a minute. So Composite is a design pattern that tries to implement a behavior in terms of smaller classes that can be combined together to give a larger, more complex behavior in terms of some smaller pieces that sometimes we don't want to, we don't care that of the idiosyncrasies of one individual object, that we would like to treat it as if it were just one. Right? It's also useful when the objects can be considered individually, right? Where we have an API that allows me to treat the individual object just the same way I can treat a collection of the same type of objects. Right? That it's the same API for either one, right? Where perhaps I want to treat a set of an individual menu, right? Or a set of menus, right? Or I have a long list of items. I like to be able to treat the item individually, or I like to treat them as a collection of items. Right? I can, so for instance, I can remove one item, or I can remove the entire list of items. So presumably, I would like for them to be both of them implement the interface or abstract method remove, right? So if it's on the individual one, I like to be able to remove that one single item. But if it's on the collection, it's interpreted as removing all the list plus all the children inside of it, right? So I like to, it's oftentimes that I like to be able to treat them as one. I don't care if it's individual or a collection, right? So the composite allows me to treat this again as a single element component, right? Or a composite that has a hierarchy of these components, where you might have a component that can be treated all by itself, right? Or a component that has a self-reference here, where the component can have children of itself, right? Notice that the component here composite here is inheriting from the component, right? And the component can either all be by itself, or it can have children of itself, right? And the client interacts with the base component, doesn't really know the implementation of the underlying composite that implements the actual component, right? Yeah, so there'll be some operations that can be interpreted on its own, like remove, right? So it could be interpreted as to remove one single component or remove an entire collection of components, or it can be treated as a leaf. Maybe it could be a hierarchy where the leaves are individual children, right? Or they could be anywhere in a node where they're a branch in a hierarchy, right? So typically, like file systems, you can list a particular path, right? And that path can be either one single file, or it can be a directory. Right? It could be a single file. But typically the API would allow you to ask, is this an individual file or is this a directory? Right? If it's a file, I like to know the name, the size, and whatnot. If it's a directory, I like to, well, I also want to know the name, right? But I can then now operate and say, well, give me your children, right? Give me whoever's below you, right? So a composite allow you to group together a lot of operations that would apply to both, either the individual or the collection. Right. So where you have either the individual leaf, right, or any branches that might contain the component itself plus the children underneath. So let's take a look at an example implementation. So as an example, we're going to use a file system, right, where we can open up a file and either list the single file or list if it's a directory, you'd like to know what children are in that file. Either you can do it recursively, right, where you can apply lists to each one of them, and so that you can apply operations such as find, remove, list. So there's a lot of operations that can be applicable to equally applicable to either a single file or a collection of files, right, as a directory. So let's take a look at this operation find. Although there's a plethora of functions that are equally applicable to an individual file or multiple files. But let's just take find as an example for finding directories and files in a file system, where the file would be the leaf, but the directory would be the composite, right? But all operations are equally likely applicable to both. So here's an example of creating, of using our API, where we have a main that grabs a directory, root directory, and several branches and several leaves. Here we have the root. We have user that is it's a directory that contains several other directories and files. So, for instance, here we're having we're saying that root is the root, and that user is a child of root, and core is also a child of root, but it's a file, so it's a leaf. Right, so it ends there. Then we have admin is a file whose parent is user. Then we have a directory foo whose parent is user. We have a couple of files that have user as its parent, and finally we have another directory whose user is the parent. And then we would like to be able to ask and apply find, and it would equally likely be applicable to a file or to a leaf, right? And we can look for either a file or directory. Right? So we like the API to be flexible enough to both be applicable to the composite or the leaves. Right? So let's take a look at the implementation. So this is what it would print. It would be looking for a bar, right? BAR. It would find several of these, X bar 2, Y bar, and bar 1. Right? So it would display those three options. So as an implementation, we're gonna be creating this abstract class that represents an abstract node in that can serve as both as a branch, or it can serve also as a leaf. Right. So this is going to be our kind of like our composite that can treat we can apply find equally likely to all the nodes, right? Either branches or leaves. We have the name, whether it's a directory, whether it's a file, and also if it's any one of these nodes can be part of some hierarchical structure where you have a root and then a whole bunch of children or branches that generate the structure. So files extends node, right? So it's going to implement those operations, as a file, it's not going to have any children, right? It's not going to have any children. So that means that it's just going to check to see if the name of the file matches what you're looking for, and if it is, it's going to return the single element, right? It's just me. I am equal to what you're looking for, and so I'll return the list of strings that it just includes just me, right? If this were a directory, instead it would recursively apply it to all the children, right, that are inside of that directory, and instead it would instead find multiple instances of directories and files that match the string that you're finding. So notice that we can implement find because we are extending node, right? So directory would be the same. The directory would also extend node, right? It would be applying the same exact functions, right? Same directory, get absolute name. Additionally, it will have add, right, which files won't have, right? But directories will. But the implementation of the find will be slightly different, right? Slightly different because we are a directory. We have children, so we can recursively ask our children to find. First we'll check to see if we match, right? Looking at our absolute name. If our name matches what you're looking for, we'll add ourselves, but we'll recursively go through all our children to find themselves. Right? And our children could be, they're nodes, right? They're nodes, and so that node could either be a file or could be a directory, and both of them implement find. So if it's a directory, it will add itself if it matches. If it doesn't match, it won't add itself, and instead it'll go and iterate over the children. If those children are directories, again, it'll just recursively go through the file system looking for these names that match. Okay. So what it allows you to do is that from the client's point of view, you don't have to think about whether a particular composite is implementing these things, right? So it kind of generalizes the algorithm, so that from the client's point of view, you don't have to remember that if it's a directory you treat it one way, if it's a file you treat it some other way, right? So always look for these hierarchies, especially when you have these nested hierarchies, right? It's a very good chance of applying this design pattern, right? That you can treat either the individual or the collection as one. Right? Which operations you could generalize so that they can both be treated uniformly. Now the ordering in this case we're using what are we using for? Yeah, a list of strings, and those will be implemented as array lists in this case. I mean, that's and array lists have a specific way of iterating over it. Right? In this case, we're using for because it implements the iterator pattern, right? But if we were using arrays or using some other implementation, then it would be specific to that particular implementation for the collection. Here, it's easy because it implements the iterator pattern. Right? So that certainly is a consideration, right? That to generalize how you're going to iterate over this, ideally the collection that you choose, in this case we use ArrayList, right? But whatever collection you choose to actually implement this, it should use the iterator pattern. Right? We'll look at the iterator pattern in a minute, but it generalizes the way you loop through all the elements in a collection. Also all these instances. In this case, you have one instance per file, one instance per directory, right? And you created a priori, right? You create the entire file structure. Typically, that's very memory intensive. You know, if you have to generate the data structure first, right, to then be able to find through this, right? It would be very, very expensive. Imagine that you know, to be able to query this find, right? You would have to build the entire data set before you can apply the find method, right? That would be very, very expensive. It's like you know, asking a program that you're going to do a SQL query, but before you do the SQL query, you need to load the entire database in memory to then do the query. That makes no sense, right? So typically all of these would have to be implemented kind of like on demand, where you load these things on demand, right, as opposed to loading everything into memory, right? So there's a lot of caching issues that you would have to take into account. Also, you know, as you iterate through recursively, recursion is very memory intensive, right? You have to maintain a stack to know where you were, and there's a lot of duplicity of things being instantiated and removed, and instantiated again, and then removed again. So it's very, very memory intensive. A lot of computation goes along. So other design patterns such as flyweight, you know, would allow you to cache things that you know, instead of reinstantiating and throwing it away and then reinstantiating it, you would keep track of these things, perhaps in a hash map, right? That would allow you to retrieve it easily, and you first check to see if it's in the cache. If it's there, you would not reinstantiate it again, right? You know, these design patterns are very common, where you have, you know, multiple instances of the same object over and over and over. For instance, it's very common when you use like a word processor, right? That you might have this flyweight I'm talking about, where you have the same letter A or letter B, or, you know, a particular letter, you know, instantiated, you know, thousands of times, right? It would be very, very expensive to, you know, maintain the same data structure represented thousands of times. So instead, you know, typically in those kinds of implementation, you only have it instantiated once, right? And then you have you know, very light references to this one, you know, particular letter, right? That has the same format, the same font, the same size, the same, you know, foreground color, the same whatever, right? If you have different A's, right, then yes, you would have different instances of those A's for different formatting, right? But again, you would not instantiate them more than once, right? More than you need to. Then you would have you apply the flyweight design patterns for efficiency, right? If you're sharing the same instance over and over across multiple times. So certainly a design pattern can, you know, a particular design pattern oftentimes is used along with several other design patterns for, you know, for improving efficiency and whatnot. So proxy design patterns, you know, are useful when you either don't have the access to some remote resource, but instead you need to have a local instance that represents or takes the place of that resource, right? And provides you typically with a very thin layer where the logic is not implemented in the proxy, but instead the proxy makes calls to the remote implementation where the business logic is actually implemented, but it's a local implementation that you can use and instantiate locally for yourself. It's very, very common when you have networks that are not necessarily readily accessible, and you create a proxy server that can just echo requests that you would not otherwise be able to do yourself. Right? You typically have like a proxy server that you send the request, and the only thing that the proxy does is just echoes your response, your request out in the network, right? And then the response when it comes back, untainted, the proxy would not do anything. The only thing is that it would echo it back to the original originator of the request. Also, it was very, very common when as a proxy objects to a database where you're talking to a local object that's it's only proxying communications to a remote database, right? And it's encapsulating some some very minor state information on whether the local data model has changed or not, and we'll do some optimizations on whether we actually need to go to the remote server, right? For instance, if you haven't done any modifications to the proxy object, local proxy object, it would not make sense to make any remote calls to a database, right? Until you actually make any updates to the local proxy object. When you make changes to the proxy object, then any changes would be synchronized and sent over to the server for synchronization of the database, right? So these proxy objects can detect changes in that state, right? And then make calls to the remote server. Typically, these would be very, very expensive objects to maintain locally, and instead we use this kind of like this surrogate object as a placeholder. So here's a class diagram that kind of captures this idea where the client is talking to this generic object that is implemented by the proxy, who's going to actually generate the request to the real to the real producer of these objects. So there's you send your request to this abstract class or this abstract interface, and this proxy can do maybe a little bit of massaging perhaps. If it's doing a massaging, then maybe it would be an adapter or facade, right? Proxy would do very, very minor validation perhaps, maybe do some caching, and then decide whether it needs to send the methods to the remote or the real subject. Okay, so here's an example, again using the same domain example that we've been using on the file system, and using the notion that on the file system we have kind of this idea of the surrogate where we manipulate a file that is not the actual file, right? That we manipulate a virtual file that might be a link to something that doesn't even live on our file system, right? That might be referencing a file system that is a remote file system, that we have some symbolic drive that has been mounted on our file system, right? That is actually lives somewhere else in the network, right? That from our point of view is a real file, right, or a real directory from our point of view, from the client's point of view. But in truth, right, it's actually any operations that you do on that virtual or fake file are being proxied to a remote system, right? So here we have the example of having a symbolic link in Unix, where we create a local proxy for some real file that lives elsewhere on the file system, and our find operation needs to be smart, right? To be able to detect whether this is a real file that we're looking at, or is this a directory, a real directory in the local file system? But if it's not, right, I need to be smart and actually make a network connection, right, and talk to some other file system in the elsewhere, right? So my find operation would have to be configurable to be smart enough to know whether do I stop and not continue and follow this fake reference, or should I do this very, very expensive call, right, into something that doesn't live locally but lives remotely. So let's follow this this analogy of the file system and see how it would be implemented using proxy. So same implementation as we had earlier. Right, we have a file system, we have a root directory and directories and files and leaves and whatnot. But some leaves, right? Some leaves are going to be links, right? Links referencing something, right? Where presumably these are not going to be real directories or real files, right? They're actually going to refer to something else. So in this case, we're creating a link. New link called link that connects the user to the root, and here's another one going from link to the root. So let's see how that looks graphically. So we have the connection of the root that connects the root to the link. First we did the first one, right? Going from the root to the link, and the link to the user. So it's the parent is the root, and the child is the user. Right? It's referencing user. And so this is the interpretation here, right? So that's the parent is root. So I'm creating a new link that is referencing user, and its parent is root. And here's another one is referencing the link, and its parent is root. So when we were asked to look for bar, right? Certainly makes sense to traverse all the nodes, but it's not clear whether we want to follow these fake links, right? So we would need to be able to configure whether we actually want them to follow these fake links or not, because they might be much more expensive. Right, that we need to do a remote connection to some remote system. We don't have that here, obviously. Right, it's all in memory. But nevertheless, the point is that it might be linked to something that is not real. It's actually proxying to something that is fake. So the vector implementation of find of the link would be the same as that we had where is it that results via link, right? So we are iterating over the results. Real node. Wait a minute. Where is the vector? This is for the link, right? Okay, so it's first comparing the name of the link itself, right? If it is, then we are adding it here. But then we have a we're iterating over the okay, there it is, right? The real node, the real node that it's actually pointing to. This could be a file, right, or it could be a directory, right? And so in this case, it would return either one or multiple vectors. And here we would iterate. If it's just one, right, we would then just go down to one level. If it's multiple, then we would have to iterate over the entire set of children if this were a directory, right? Right. So we've extended the implementation of link, which is fairly similar to the one for a directory. Oh, okay. Some other patterns are deal with how the classes might behave, or how things we implement iteration, or how we might also notify of different events. Typically, the way we've handled these things like iteration is that we control the iteration. The parent controls the iteration, right? We know from where we're starting. We know how many times we're going to loop, or we have a predicate, and we know that up until the predicate is, as long as the predicate is true, we're going to stay inside of the loop. So it's a parent's responsibility to handle the iteration, right? And so there are many different other ways that we should consider, where the parent perhaps can delegate the iteration to the child. It says, well, I don't know how to iterate over you, but you know how to iterate over yourself, right? And I can call on a function that knows how to iterate over that data structure, so that the parent is no longer responsible of knowing how to iterate over the child. It is the child who iterates over themselves, and then just notifies the parent every time it's going through that loop, right? So we kind of like invert the responsibility of iteration, right? Or depending on the data structure, if it's a linked list, if it's a hash table, if it's just a plain array, the way that you iterate over these data structures is different. Right? So typically we want to unburden the client or whoever's using this data structure of having to treat it one way or another. Right? Instead, we want to generalize the concept of just going through one element at a time. Right? So those two big ideas. One, I want to generalize the way I can go through each element, or I don't want to even bother having to know how to iterate over you. I'm going to instead delegate it to the child, right? And it will be the child's responsibility to iterate over itself and notify me, every time I have an item. Right? So those two big ideas, or even this notion of notification, right? That's typically a very hard thing to handle on an application. How is it that different parts of the application talks to other parts of the application? Typically the common way of sending events from one part of the application to another part of it is to typically I need a reference to you, right, so that I can call you when something happens, right? That I need a reference to you, and so typically what we like to be able to do is that somewhat reverse that somehow the person who wants to be notified instead should register, right, and show interest. That it wants to be notified of these events, as opposed to as a parent having to know, right, that I need to instantiate all these folks because I need to notify them. Right? Instead of the parent needing to keep track of who to want to notify, the child can then notify the parent. Hey, parent, I want to be notified. Right? So it's kind of reversing the responsibility there. Right? Obviously, it will still be the parent who notifies the children. But it won't be the parent's responsibility of knowing who they are. It will be the children's responsibility of registering with the parents. So it's kind of reversing that role. Anyway, there's tons of these. The template method, where you might give it a very generic method that has most of the algorithm implemented. And then maybe a small portion of it, it would be the responsibility of the children, right? Where the parent, gives it a 90% of the algorithm all hashed out, implemented in a method, but then leaves the other 10% up to the children to go on and hash out the rest. Memento that allows you to oftentimes we have objects that come to life, and then they're destroyed, and then come to life again, and then destroyed. Oftentimes we'd like to be able to not destroy them, but maybe put them to sleep, or put them away for a second, maybe in a file system, and we would like to maybe revive them at a later time, without going through the overhead of having to instantiate these objects. Oftentimes these might be objects that are very expensive, right? So instead of going through the overhead of reinstantiation, we might put them to sleep on the file system, and then we would like to revive them. And so oftentimes to be able to do that, the object needs to. Typically, these objects are all the state information is private, right? All the state is private, and we don't have access from the outside, right? But so if we don't have access to its state, how are we going to store it to revive it later on, right? So somehow we would need to have access to its internal state, right? Enough of it that we can put it to sleep, and then reconstitute the instance from its original state, right? So Memento allows us to have these enough state or enough visibility into private state information, enough that we can reconstitute. Anyway, there's tons of these. Let's take a look at these. Some of them. So first, iterator. So iterator. Two ideas. One of them, who is responsible for the iteration? We would like to maybe be able to reverse that, and also, I don't want to be burdened with with knowing the specifics of how you're implemented underneath. Right? I don't want to know that you're a linked list. I don't want to know that you're a collection or array list. And so instead, I want to talk to you and iterate over you independently on how you're actually implemented underneath. Right? So what we want is some generic interface, like an iterator interface, that declares these generic functions, like give me the first, give me the last, maybe, give me the next one. I want to know when I'm done, right? And go on to the next one. You can enhance this so that it might provide other things, such as, well, I want to jump randomly to a particular position, maybe, right? But those typically might be expensive, right? Depending on the implementation, right? If it's using contiguous memory locations, such as an array, then jumping randomly from one position to the next might be inexpensive, right? But if the local implementation is a linked list, then that might be very, very expensive, right? So typically, we discourage random access, right? And instead, we provide this very generic implementation that all most all collections should implement. Then internally, the concrete iterator will actually use the concrete aggregate. The concrete aggregate knows the actual implementation, whether it use arrays, whether it use linked lists, whatever it uses, it knows the actual iterator that it needs, right? And the concrete iterator actually uses the base implementation, knows the idiosyncrasies of the actual data structure that you use to implement it, right? But from the client's point of view, it doesn't know any of that, right? It has this very generic aggregate, which you can give it the correct instance of the iterator, and the client only has access to these 4 or 5 methods that are then implemented by the concrete iterator. So here's an example that one of these nodes it wants to iterate over the children, right? Or iterate recursively, starting at the at that particular node. Then you can ask for the iterator. Here's the iterator, right? It's parameterized, a parameterized iterator, and we're using the 3 or 4 functions of getting starting at the first, initializing the for loop, then asking whether we're done, and otherwise just advancing to the next element, and then retrieving the current. A very common another example that where the iterators are very useful is iterating over an extremely long collection, right? That there's no way you could possibly have the entire collection instantiated in memory, right? For instance, if you do a query to a database, right, and the select statement comes back with 10,000 records, right? It would be it would be unrealistic to instantiate 10,000 instances in memory, right? If you're just going to iterate over the first 100, say, it would be a complete waste of memory, and inefficient. So typically the way those types of iterations occur is that the iterators know that they're going to have a cache of maybe 100 elements at a time, perhaps, and they're going to fetch the first 100 records into memory. And as you iteate and you advance the cursor in memory, as it approaches the last 90% of the iteration, it will do another query, right, for the next 100 records, right, and into memory, and we'll throw away the first 50 or so, right. So it will have a running set of 100 of caching that as far as you're concerned, you feel like you're iterating over all the 10,000 records, right? You never knew that underneath all this magic is happening, right? That I have a live connection to a database. I'm fetching, 10 or 20 or 30, depending. You can configure how much you want to go fetch, right? The cache that you have, and all this is happening, right? It looks as if you're iterating over the entire data set, but underneath a lot of things are happening, right, to make it so, right? So very, very useful. And underneath it could be that this came back with thousands of file elements, right? Individual files. It would make no sense, right, to instantiate thousands of these file leafs. Right. Instead, internally, you would have some cache mechanism that would periodically, as you're iterating, it would fetch another 10 or 20 files. Right. We go out to the file system and retrieve the next 10, the next 10, the next 20, right? Depending how you. Typically, these iterators can be would allow you to. Some more modern implementations would allow you to not just go forward, right, but also go backwards, right, or jump to the last one, or jump to the first one. Some iterators can be enhanced in such a way that once you have an instance, right, you can then operate on that instance, and as you operate on them, then any changes in the state, using a memento design pattern, right? The state can then be synchronized back to the original instance. Right? So any operations that you're like, for instance, you're iterating over a result set that match a record in the database, right? And as you're iterating your particular record, and if you update that record, any state changes that you make, the iterator knows that it needs to do an update back to the database, right? And it synchronizes whatever record you have in memory with whatever record you might have in the database. So yes, I mean there's certainly lots and lots of really cool things that you can do with an iterator. You can enhance this as much as you want. So anyway, so this is the bare bones implementation of the iterator that allows us to go forwards, only forwards. Some iterators will allow you to also jump to the last, right? So last, first, next, previous is done, or ask for the size or the count. How many elements are there that I'm going to iterate over, right? Some of them allow you to paginate and say, well, I want to skip by. So they might have a function called skip, right, that allows you to skip 10 at a time, right, and just go through there. Or maybe like a limit that allows me to say, well, I'm going to skip to the 100th element, and then I want 100 of those. Right? I want to iterate over the next 100. So yeah. Anyway, so this is the bare bones declaration implement of an interface. And here we would have an iterator for the directory, which might have a list of nodes that. Let's see, directory extends node has an iterator. So the iterator is the function that you call to get the iterator over this data type. So in this case, it's instantiating a local private class that implements the iterator interface. So it provides access to the next, done, right? All those. Internally, what it does is that it declares a local instance of all the files in that directory, right? And how many there are, based on the directory that you pass as an argument. In this case, it's this, right? It's passing an instance of the directory, and it grabs the children from the parent directory. And then here are the implementation for each one of these. The first, the file count kind of tells me where I am in that particular iteration. Current, it goes and actually fetches the actual file for that particular count. Is done. It allows you to just check to see if the count has reached the size of the number of children that you have in there. So remember that I mentioned that iterators typically have either delegates the iteration to the parent, right, who has control over the iteration, right? Starts with the first, it checks to see if it's done, right? It navigates to the next one, right? And then it retrieves the existing current, or instead of the parent being responsible for the iteration, it can delegate it to the collection itself. It says, well, I don't want to iterate. I don't want to handle any of that. Instead, I provide several functions, right, that know how to iterate over the underlying data structure, and then I provide some kind of callback that as it's iterating over the collection, it can notify me every time it finds a new item or a new element in the collection, and it passes it to me as a callback, and then I can do whatever I want with it. I can compare it, I can increment it, I can update it somehow, right? And I can manipulate it. But notice that as a client of the collection, it's not my responsibility to iterate over this. Right? I have delegated that responsibility to the collection itself, right? And I have no control over it. Well, actually, no, that's not true. I could enhance the item, right, to have some control over the iteration, right? Maybe based on the return type of this function, I can abort the iteration, right? If I return, if I return null, say, then that might be interpreted by the parent iterator, right? By the parent function that's iterating as an abort, stop the iteration. I don't want to continue the iteration, right? Or it might give me additionally other arguments that might allow me to do aggregates, right? Aggregations that say I want to do a sum, right? So it would pass me additional meta variables that would allow me to aggregate the value on those variables that are being passed to me, right? So anyway, so the implementation would be obviously dependent on the collection itself. Whereas external iterators is they're basically the ones we've looked at, right? It's the parent who has full control over the iteration, now obviously when you have control over the iteration, there's always the danger that the iteration is changing as you're iterating over it, right? That either you or some other thread might be adding elements or removing elements, or even you as you're iterating, by deleting an element of the iteration. So the size is changing as you're iterating, so you're no longer iterating over the original collection, right? Let's see. So yeah. So be careful with remove operations that would change the original state of the iterator, and some of these iterators disallow, right, that you apply certain functions, that the iterator is immutable, right? You cannot mutate the original collection as you're iterating. So you would not be able to to remove an element as you're iterating, right? Because it would change the original collection. Observer is the idea of being able to manage in a better way communications across multiple parts of the application, and it has become very, very useful in many of newer frameworks. Right, it's widely used certainly in front-end development, and also in user interface in general. User interface in general are use the observer pattern widely, where one portion of the application would like to be notified if something happens elsewhere, right? And so typically different portions of the applications that have register themselves, with a particular object, and say, hey, object, if you change, if something happens to you, I want to know. Right? So notify me. And so instead of the object having the responsibility of going and finding out, if I change, I need to go and notify these folks, we reverse that responsibility of anyone who wants to be notified, tell the object that you want to be notified when the state changes. Right? It's widely used in front-end development. For instance, Angular is really, really big on this. You can register a callback on basically on any user interface elements, right? That if the input field changes, or if the drop-down changes, or as you're interacting, there's a lot of folks who have registered interest in this particular event, right? And these UI objects will notify anybody who has registered interest. So using the observer pattern, so it has become widely used in modern UI development. Anyway, so in an observer, right? It shows interest in some event or some state of somebody else, right? Some subject, and what it does is that the observer calls on the subject, saying, "Hey, I'm an observer, and please let me know. Notify me if your state changes." And typically it does it either by attaching and detaching, right? And so the way it would happen is that that when the state changes of the subject, it would notify it would iterate over a list of observers and call and say, hey, I changed. You told me that you wanted to know, right? I'm calling you, and they would implement a particular interface such as update, right, or notify, or whatever, right? And then so the actual class would need to implement that interface, right? And then it would be able to call on the original subject the methods such as the get to state or set to state and manipulate them. Okay. So internally, the notify would iterate over all the observers calling their update method. So again, this is a very widely used design pattern. So here's a sequence diagram that kind of illustrates the way the mechanism works. You have the subject, the observer. Wait a minute, let's notify concrete observer update. Update, set state, notify. Okay, so the concrete subject does a notify and then calls on the an update method on the concrete observers, and there might be multiple observers. It can be any number of observers. So here's iterating through a loop through each one of the observers, calling their update method, and then the observers can then call back to the object and says, okay, well, what is that change? What is the new state? And then it retrieves it. Okay. So what happens here is that notice that it's a concrete observer that kind of changed the state, right? It set the state, and then anybody who had registered an interest in that state gets notified in some loop. So let's look at an example of an observer for instance, a file. That if a file changes, if you write to the file, or if you delete the file, or if anything happens to the file, we would like to be notified across the framework. Right. So we're going to create first an observer interface that all observers are going to implement, and they will be notified through the update method. Use the file observer that implements the observer. And it declares functions such as attach, detach, notify, and update. So anybody who wants to listen or wants to would implement this interface, and it would attach itself to the file, right? And then be notified if the file changes because the update will be called. So the file, if it changes, is going to call this update function. So let's take a look at this. So here's the node, right? That we're enhancing the node by adding these two functions, attach observer and detach observer, implemented as a just plain old array list of observers, which we don't have here. There it is. So here's our list of observers, and what we're going to do is that if in our call to update the state of this file, if we're writing to it or deleting the file, we would then notify the observers by iterating over the observers and calling their update function. Okay. In main here we have a file that we're creating, and when we write to the file, all the observers are notified. Visitor is also a widely used design pattern that we have. We want to encapsulate some algorithm that wants to be applicable over a collection, a long collection, and we want to generalize the way that the way we pass along these algorithms, and then be applicable to all the items in the collection. So we have a visitor that has different operations that you can call on it that would be implemented by concrete visitors, and then you would apply to an element and say, hey, element, here's a visitor, and within that visitor, the visitor would call the visit A, which would be implemented by the concrete visitor. Okay, so let's take a look at an example. The client would ask a concrete element that hey, here's a visitor that has certain operations, and whenever and then it would use the functions that are declared there, such as visit A, visit B, on it to call in on itself on the concrete visitor. It would call the operation. We wouldn't know what the actual operation is. That would be hidden by the concrete visitor. We don't have access to that. We only have access to the visitor that would pass along. So this would be hidden from us, right? This would not be accessible to us. It would be an implementation specific to the concrete visitors, right? And it would say, okay, well, here are the operation. I want to pass it along and apply it to this concrete visitors. So here's an example that we would like to pass along to either a single file or a collection of files, a visitor that is going to count the size of the directories and the subdirectories. Kind of using what the du function does in Unix. So here's a file and the link and the directory. They're all going to implement this accept function. Right? They're all going to implement it in their own way. So here's the visitor, and the visitor has a function called visit, right? Which implements some logic that we want to apply on every single node that we pass it to. So instead of implementing it here in the link and the file, right? Otherwise, the behavior for visit would have to live in link or would have to live in file. Instead, what we're doing here is that the actual operation does not live in the node or the file or the link or the directory. It lives elsewhere, right? Instead, we're kind of inverting the responsibility of implementing these visit functions, right? Directory has a slightly different implementation. It calls its visit, right, on itself, and then it then passes along the same visitor to all the children who are going to visit themselves, right? They're going to recursively go down the line, for every single directory, all the way down to the leaves, right, in the directory structure, right? So it will visit every single node until it reaches the leaf, right, recursively. They're all implementing the same visitor interface, and notice that the visit function is overloaded, right? So that depending on the data type that you pass it, right? If you pass it a file or a directory or a link, it'll be implemented differently, right? If it's a file, it might just look at the size of the file, right? And that's what it returns, right? Instead, if it's a directory doesn't have a size. Instead, the size will be the summation of all the sizes of all the children, right? That will recurse all the way down, right? And then it will bubble up with the size of all the children. Yes, so it's quite different. A link, I guess, it would be the same thing. It would be recursed depending if it's a directory or a file. So the actual implementations of the concrete visitors will be different. So the du visitor, it's implementing visitor, and the actual implementations for the file, it will look at the size of the file and just return the size of the file. Updating static values for the du visitor, whereas visit, it'll just count how many links there are. Whereas in the directory, it will recursively. I'm sorry. It just counts the name of directories. Okay, I thought it was going to go and recursively go down the directories. And at the end, right, it just reports the number of files, the number of directories, links, and total size. Okay. And that's the client. State is when the logic the logic becomes fairly hard to encode, and the state of the application changes over time. Oftentimes, it's easier to model that as a state machine, right? Where you have a piece of code, a piece of a class or object, right? That changes its state over time, and from very discrete, representable, maybe a numerator from some kind of enumerated data type, and depending on that particular state, you encode certain behaviors that follow that particular state. Now, the typical way of implementing it would be to use all sorts of switch case statements that would make the implementation fairly brittle. So here's a trivial example of a vending machine that you can purchase items by or a product with 25 cents, but you can feed it with nickels, dimes, and quarters, so it needs to keep track, right, of how much money it's got. If it has reached 25 cents, if it has, then it will dispense the product, or if it hasn't reached it yet, right, it kind of goes through several states until it reaches at least 25 cents, and then if it has gone above, it needs to return a refund. So here's a state machine that we could use to implement this trivial vending machine. It starts at that you don't have any money, you haven't yet put in any money in there. Excuse me. And as you deposit either a nickel or dime or a quarter, right? It goes through these distinct states, right? So first there's nothing. If you can either enter the entire 25 cents or a quarter. Well, I guess I don't have it here. Oh, there it is. If you add a quarter, right, then you dispense the product and you're done, right? But if you go back to the credit zero. But other than that, you can either put in a nickel or a dime, and that puts you either in state 5 or state 10. From state 10, you can add yet another dime or nickel or a quarter, right? If you add a quarter, then you have immediately reached your limit, right? And you can just dispense the product and go back to and give back $10. 10 cents, and dispense the product. Or if you instead have giving a nickel or dime, you've either jumped to 15 or jumped to 20, and again, different things might happen. Okay, make sense? You're pretty simple. So this has kind of like a traditional way of implementing this. So here's a vending machine that has some base implementation for some interacting with the user, displaying the welcome or dispensing the product, and being initialized with a balance. So when you instantiate it, says welcome, balance is set to 0, and kind of balance will be our state. Okay, and the balance will be able to jump from 0 to 5 or 0 to 10 or 0 to 25, or depending how much you're putting in, and depending on the balance, we would decide what to do. So one common way to do it is here's a display, here's a refund. Here's a very common, very easy way to implement it. If the balance, if you add a nickel. If you were in 0, you become 5. If you were in 5, you become 10. If you're in 10, you become 15, and whatnot. In other case, in any of these cases, we just we change to the next state: 5, 10, 15, 20. We display the balance. We haven't reached yet 25, right? So we always display the balance. If we were already at 20 and we add a nickel, then certainly we've reached 25. We dispense the product. We go back to 0. We say welcome, and we break. But in any of the other cases, we've come up short. Right? We don't have enough. If we have a dime, it's kind of the same thing. But the jump is a little bit different. If we were 0, we want to go to 10. If we're 5, 15, from 10 to 20. If we're already at 15, we've reached. If we're either at 15 or 20. We already reach our goal. We either go back to 0 and dispense. In both cases, we dispense the product. But if we're already at 20, we're going to refund 5, right, because we went overboard. And finally, quarters, same kind of thing. But lots and lots of switch case statement. If we ever need to change the state diagram, we're going to have to go back and modify all these switch statements, right? We would have to modify all 3 functions. It's very interdependent between the two. We have this logic spread out across multiple functions, and it's very hard to add new states, right? All functions would have to be changed. So there's a very close, tight coupling between the knowing exactly all these states in the transition. So here's a client where using the vending machine and calls the different functions and it transitions through multiple of these, and at the end, you give way too much, right? We dispense and then we give you back some cents. So this is what it would print, right? It says the balance 5, 15, 20. We dispense and then we give back 20 cents because we were over by 20 cents. Please enter 25 to buy product. So the behavior is kind of spread out across multiple functions. So it's very hard to add. If you want to change the state, if you want to add new states, or if you want to change the logic of how this transitions, it's very, very hard to do. So instead, what we could do is use the state design pattern, where you kind of decouple this so that it'll make it easier to add new states as you see fit. There won't be any limitations on the state. We kind of give back. We switch the responsibility of, instead of having the parent know the transitions and where he should go, instead we delegate that to each one of the states. The states know what should happen, right? As opposed to the functions knowing what happens, right? Instead of the parent knowing what should happen, each one of the states know what should happen. Right? So we're switching the responsibility. So here we have the vending machine state. So we're declaring a state. The state will know what should happen when different events occur. Right? So the state says, here's each one of the state, and each state knows that the only way to transition out of a state is whether we add a nickel, we either a dime or a quarter. Okay, and so it has its way of leaving, and any new state that we add, if we want to add other ways of transitioning, we have a single place to add that transition, right? And immediately you have all the other states inheriting from this base state. Okay, all base states, all derived base states would inherit from this. Each one of them would implement it differently, okay? But it would be easy to just add additional states. So let's for instance, here's one of the state, credit 0. That's one of the states. Notice that it's implementing the vending machine state, and it instantiates has a static value of type credit 0, so the instance. So I'm keeping track of myself, right? And it instantiates itself. So in static, when we first call this, right, it instantiates itself. It kind of keeps track of a singleton. It's kind of like a singleton design pattern, right? It has its own instance, and then also notice that in the instance, notice that we're passing here. We're passing an instance of the vending machine. See that? each state is going to have an instance of the parent, right? It's going to have an instance of the parent, and it's going to keep that instance here. V, right, so here it is, so V welcome, so we can immediately call the welcome on this, okay? Then as being credit 0, I implement my at nickel, dime, and at quarter and balance. What we do is that at each step of the transition, we're always passing an instance of the parent vending machine. We could have passed it as an argument to the constructor. Could have done that. Here we're passing it every time. And what we do is that we tell the parent, says, hey, we're going to change to a different state, credit 5. So if we add a nickel, we go to credit 5. If we add a dime, we go back to credit 10, or if we add a quarter, we've gone too far. We're going to dispense the product and then go to credit 0, right? And the balance is 0 because we are in the state credit 0. So credit 20. Obviously, we would have credit 0, 10, 15, 20, 25. Right? I'm just skipping around here. Here's 20. We would have an instance of 20, and then we would implement the at nickel, at dime, at quarter slightly different. Right? We would notify the parent vending machine that the state has changed. Right? Notice that the inversion, right? It used to be the vending machine who knew how the states would change. Instead, we're delegating those to the states themselves, right? So we're kind of inverting the responsibility here. And a lot of the new design patterns today are this notion of inverting who is responsible for this, right? Inversion of control. It's one that has become the auto wire, right? The hash. Give me an instance of this data source, right? I no longer want to be responsible for these things, right? Instead, I'm delegating these to the infrastructure. Somehow magically somebody is handling this. So here's the magic. Here is since I'm delegating to the children are handling these things. Somebody has to do it, right? So anyway, stage change. The vending machine. The vending machine is maintaining the current state, right? The vending machine state. So the vending machine still knows what the current state is, but it is not changing the state, right? Instead, it is the state themselves that come back to me and tell me who the state is, right? At initial point, when it gets instantiated, it will default to the credit 0 instance. But as each one of the state goes across multiple state, as different dimes and nickels get deposited, each one of them will call back to the vending machine and will pass to the new state, right? So if you were at balance 0 and you put a dime, then the balance 0 state will call the vending machine to change the state to be the state, the 5, the dime state, right? And we'll display the balance. So internally, it declares these functions at nickel, but it itself doesn't implement it. Instead, it delegates to each one of the states, right? So the current state at nickel, and it passes an instance of itself, right? So that state underscore state will be credit 0, credit 5, credit 10, credit 15, the different states, and each one will know how to implement the at nickel, at dime, and at quarter, right? It is no longer the responsibility of the vending machine, right? It delegates it on each one of the states. There's tons of of patterns. We could be here all night. Memento strategy. I mentioned these early on. Some other things is that obviously not every problem has a. You should just go crazy and start looking for patterns immediately. They'll come to you or as part of the team, you will be discovering these patterns. As this is a good chance to apply this design pattern here and there. And oftentimes it comes up as a refactoring effort, right? Code that has been there for a while, and you might identify these patterns as you become more familiar, you're more understanding of the code, and then you can identify and actually apply them. Okay. All right, let's take a quick break, and we'll come back after these messages.